Hello, beautiful calculus people. Welcome to a pre-recorded lesson for your Wednesday class. My apologies for not being able to host a live class today. I will be able to hopefully catch up with you guys next week. I'm hoping that this week isn't too big of a deal. We don't have a lot going on other than maybe the quiz that's due on Friday. So yeah, if you're running into any questions about the quiz, feel free to email me and we can set up a time to chat if that's something that you would like to do. On Monday, we were starting to talk a little bit about series and geometric series and looking at a couple things that are going to be important for us. So let's just kind of summarize some of the concepts we saw. So first and foremost, the idea of using summation notation or series notation is to kind of collapse a bunch of additions into a more simplified kind of expression. And we use sigma to do this, and typically we're using like I, or today we're going to be using n to denote an index. And that index is going to range through a bunch of whole numbers typically. And the idea here is we can kind of work both ways. If we have a really large sum of pieces, we can kind of collapse them all together into the sigma notation, or I can work in the other way. If I have sigma notation, I can use the index to kind of unravel using the formula and kind of get all of the terms in the sum that I need. So it does go both ways, and we took a look at a couple examples of how to find the formula and collapse it into sigma notation, as well as start with sigma notation and expand it out to actually find the sum of something. Now, there were a couple of formulas that we're going to come back. We are going to use these a little bit later. We're going to use these probably maybe in Friday's class or moving into next week as well. So for now, we're just going to kind of tuck those into our back pocket. This is kind of the sum of C, the sum of the first n natural numbers, the sum of the first n square numbers and cube numbers. We're going to tuck those formulas away for now. We probably aren't going to use them today. But we might see them kind of pop up either on Friday or early next week. What we may want to utilize today, depending on kind of what we get into with regards to our examples, is we may want to use the property that we can break apart a summation across addition or subtraction. So that's a helpful property that we can use. Or if we have a constant number, it's also possible to factor that constant number outside of the summation if that's a helpful thing to do. So yeah, we can factor that constant out, provided that the constant isn't something that depends on I or the index of our formula. And really, a lot of the objects we're going to be talking about over the next month are going to be infinite series and the applications of being able to utilize infinite series. So we're kind of moving away a little bit from antiderivatives. We've kind of seen a lot of applications of antiderivatives, and this is the other kind of main chunk of our course, is talking about infinite series and some of the really interesting applications of series, just kind of giving you guys an intro into this kind of world. It's a kind of a crazy world. So we have two different kinds of series. We have finite series, so a finite number of terms. We can usually add these things up and actually get a sum. And we have infinite series, where maybe our upper bound is equal to infinity. So our whole numbers keep increasing by 1, so we have an infinite number of terms. And the question was, is it possible to actually add up these infinite terms? Of course, we looked at a very obvious example where we start adding up the first n numbers, but we let the number of terms here tend towards infinity. And obviously, it doesn't make sense to talk about the sum of this thing because it is infinitely large. So just like when we were talking about sequences and improper integrals, it's possible for these infinite series to be divergent. That is, that the sum of these things tends towards positive infinity. The sum of these things could also tend towards negative infinity. So this is a divergent infinite series if we run into that particular case. And often we're going to be concerned about convergent series. So we're going to be curious or interested in whether or not it's possible to associate a sum with the particular series that we're working with. In the case that we are able to associate a number that represents the sum, we call this a convergent infinite series. And one of the big ideas we saw right away was this idea that because we're adding up stuff, we eventually want to be adding up something that's surprisingly close to zero. So one of the easy checks to do to see if something is divergent, if you have a formula, like an AI formula that's associated with our sum, the easiest checks you can do for divergence is to check that limit. So does this limit tend towards zero as the terms get really, really big? If it doesn't, then you can automatically conclude that your sum is divergent. Now, the only problem is it doesn't work in both directions, so you just have to be really careful of that. It's necessary that the limits have to tend towards zero, but that doesn't tell us the full picture. So if the limit doesn't tend towards zero, we can conclude divergence, but if the limit does tend towards zero, that doesn't necessarily mean that we have convergence. And I did give an example of an infinite sum, an infinite series, where the limit does tend towards zero, and you can take a little look at the textbook. They go through a little bit of algebra here to actually try to convince the reader that this kind of infinite sum is actually divergent. So yeah, it's a very powerful theorem when proving divergence, but doesn't give us a lot of wiggle room with regards to proving convergence, which typically is a much harder thing to do. And the last thing we took a look at in Monday's class was geometric series, because geometric series have a really nice form, and they're very, I think, straightforward once you kind of understand how they work to check whether or not they converge. We did do a little bit of work doing a little bit of proof, and we arrived at the following formula. A geometric series, provided that r is between -1 and +1, does converge, and it converges to the formula a over 1 minus r. So that is an important formula, and very similar to some of the other formulas that we talked about on Monday. This is one that you probably want to write on your formula sheet. It is going to be part of the formula sheet on your final exam as well. So I just selected 6 examples that I thought were kind of nice examples for us to kind of start talking a little bit more about series and just do a little bit of work with regards to some of these specialized series. So essentially what we're going to be doing is we're going to be determining whether or not the series converge or diverge. And if the series does converge, we're going to have a go at actually trying to figure out what the sum should be. We're going to try to see if we can find that defining number, capital L. Okay, so number 1. Let's kind of work through our 6 examples. And there's a couple techniques, I think, that are important from this section and some terminology I want you to know, and we'll kind of explore that through these examples. So the first example is going to be number 35. And this is from section 11.2. Okay, and number 35 from section 11.2 is actually going to be a sum that's given to us not with summation notation. So it's given to us as a sum of a bunch of fractions. And it's up to us to figure out if we think this is going to be a convergent kind of thing or not. So here are the first few terms of that series. And we would like to figure out if we think this is a convergent or a divergent kind of series. And typically one of the nice things you can check right away is you can kind of check to see what the ratio between terms are. So if I say call this A1, A2, A3, and A4, we could do some division. So we could take A2, for example, and divide by A1 and see what we get. So if we take A2, which is 4 over 25, and we divide it by 2/5, let's see what we get here. I'm just being like purposefully lazy tonight. Okay, so if I do that, I get 2/5. And what we want to do is we want to kind of check maybe one or two more of these divisions where we put the higher term, I guess, the term that's further to the right, over the term that's further to the left. So in our case, we can kind of double check and see what the ratio is between A3 and A2. And we're kind of checking to see if they share a common ratio. Because if they share a common ratio, this might suggest that it's a geometric kind of sequence. And I have a formula to deal with the geometric sequence, provided that the common ratio is a fraction that's in between -1 and +1. So yeah, we can go ahead, we can divide A3 by A2, and we're going to notice that we get 2/5 again. Okay, so because I'm getting the same kind of common ratio here, this is like an indication that this is likely a geometric series. So our goal is to figure out what is A and what is R. So R is going to be our common ratio. Our common ratio is 2/5, right? That's essentially what we found here by dividing the larger term. It's weird to say the larger term, but the term that's further to the right by the term that's next to it but to the left. And A here is going to represent our first term inside of the sequence, which also happens to be 2/5. So this number up here we're going to call A, and this common ratio is called R. Okay, and like I said, it's not, sometimes you can see it right away that it's a geometric series, and if not, you just want to find the ratio between your consecutive terms like this, and if they're the same, that's your indication that you are likely dealing with a geometric series. So once we know what the value of R is and that we're working with a geometric series, we want to check this common ratio. So is R in between -1 and 1, right? So that's the very first question we want to ask, because if it is, I have a formula to deal with this particular sum. If R is not in between -1 and +1, and I know it's a geometric series, then that geometric series diverges. Okay, so because R is in between -1 and +1, I know that this is a convergent geometric series. And in fact, we can just scroll up a little bit. We can get our formula. This is going to converge to A divided by 1 minus R. Okay, so this geometric series will converge to A over 1 minus R, which is 2/5, divided by 1 minus 2/5. So if we can simplify this fraction, we know exactly how to define the sum of this particular series. Let's see, what do we have? 5/5. So we have 2/5 kind of stuck here in the numerator. In the denominator, we have 5 minus 2. So that's going to be 3/5. So it looks like after we kind of do our flip and multiply here, we should get 2/3. Okay, so the sum of our initial series should be 2/3. Okay, so therefore, if we copied down this sum again, so 2/5 plus 4 20/5, 8 is 16, 6 25 is equal to 2/3. This is how we define the limit of this particular sum. Because it's a geometric series, I know it converges, and I know exactly the formula to find the limit of this particular infinite addition. Okay. So there's example number 1, just a kind of a very, I think, straightforward example with regards to working with a geometric series. Let's take a look at an example that maybe not as obvious that it's a geometric series until we do a little bit more work. So this is number 36. again from section 11.2. All of our questions are going to be from 11.2 in the text. And question 36 looks something like this. So again, it's a sum that's going to be defined by just adding a bunch of fractions together. Here's the sum we want to work with in number 2. And again, we're curious about whether or not this is going to converge to some kind of sum, or whether it diverges, whether or not we're going to actually be able to find a sum, or whether or not when we start adding up all of this stuff, we end up getting, in this case, positive infinity, because we're always adding positive numbers. By the way, it's like, I know that we usually have class at like 11 o'clock or something like that. If you're watching this early in the morning, it's actually like 11:30 at night, so I think I'm okay. I think I'm okay having that wine at 11:30 at night. Just be mindful of that. I'm not actually day drinking, not right now. Okay, so let's get back to kind of our examples here. It does look a little bit strange, right? It looks like, if I start labeling stuff like A1, A2, A3, and A4, and I start kind of trying to find these ratios, what happens? Let's see. Let's take our 2/9. Let's divide by 1/3. And I think doing this is going to give us like 6/9 or something like that. Okay, so it should give us 2/3. And if we kind of keep going, so again, I want to kind of see if the next ratio is the same. I want to see if this next ratio is also 2/3. I don't think that's going to work. So if we take A3, which is 1/27, and we divide by A2, which is 2/9, that's not going to be great for us, right? We're going to get 1/27 times 9/2. Which is 1/6, I believe. So these are not common, right? So because I don't have common numbers, the way that it's set up right now is definitely not a geometric series. But maybe you notice that every other term has a 1 in the numerator and every other term has a 2 in the numerator. So maybe we can rearrange this and check again. So maybe I can rearrange this so that all of the terms with 1 in the numerator kind of come first. And then I'm going to add to that all of the terms that have a 2 in the numerator. And then let's try this again. So let's try labeling these as, let's say, A1, A2, A3, and maybe labeling these as B1, B2, B3. So kind of thinking about these as two separate entities or two separate series that are actually getting added together. So let's go ahead and let's do A2 over A1 and see what we get. So this is 1/27 divided by 1/3, which will give us, let's see, 1/9. Okay, and let's just kind of verify by dividing the next two consecutive terms. So 1/243 divided by 1/27. And you should be able to convince yourself that this is also going to be 1/9. So we do have a common ratio here. Which is great. So because I know that R is in between -1 and +1, this is likely a geometric series that's going to converge because I know that common ratio is a fraction in between -1 and +1. So that deals with kind of like the first half of this problem. Let's take a look at the second half. Let's maybe do b2 divided by b1 and see what happens. 2 over 81, 2 over 9. Ooh, what are we going to get here? 1. Is this a 1/9 as well, I think, right? This is also going to be 1/9. Now let's go ahead, let's take b3 divided by b2. And you can probably, again, either utilize your calculator or convince yourself otherwise by just doing a little bit of algebra here, that this is also going to be 1/9. So again, we have a common ratio of r is equal to 1/9. And again, we just want to check this to make sure that it's in between -1 and +1. So I know that these are both geometric series, and I know that both of these series are going to converge. So that's a great thing to know. So let's just kind of summarize that. Therefore, both series are geometric, and both are going to converge. It's going to be helpful here to get the a values for these as well. So let's just kind of scroll back up. So over here, we're going to have a is equal to 1/3. And for our second series, we're going to have a is equal to 2/9. Okay, so those are the corresponding a values so that we can go back and utilize the formula for our convergent geometric series. Okay, so for the first series, the sum is a over 1 minus r. We said that a is equal to 1/3, and we found that the r value is 1/9. Okay, let's go ahead, let's simplify this expression. So we get 1/3 divided by, this is going to be 9 minus 1, so 8/9. So 1/3 times 9 over 8. We can maybe get rid of a factor of 3, so it looks like 3/8 is going to be our final sum over here. Okay, and then we'll use the same formula on the second series, so a over 1 minus r. Over here we said a was 2/9. That was the first term in the sequence, and we found a common ratio that was similar. The common ratio here is 1/9 as well. Okay, so this gives 2/9 over 8/9. Okay, so that's 2/9 times 9 over 8, so our 9s will cancel, and we can cancel out a factor of 4 here as well, or a factor of 2, sorry, to get 1/4. Actually, you know what, let's keep it as 2/8, because I'm going to have to add these together anyway to get 5/8. All right, so that takes care of utilizing the formula. Therefore, we know that this sum we know that this will, well, should actually probably go all the way. So all of this converges to 3/8, and all of this converges to 2/8. So our final sum should be 3/8 plus 2/8, which is 5/8. So there you go, a little bit of a different kind of example here, one where you have to do a little bit of rearranging. But both of those geometric series do converge quite nicely. Let's take a look at an example of something that doesn't converge. I think that's going to be nice to see here. So this is number 42 from the same section. This is the sum. Okay, from 1 to infinity of the following: 2 to the n plus 4 to the n over Euler's number to the n, so e to the n. Now, it may not be obvious to you right away that this diverges, And if it's not obvious, that's okay. I mean, like, it's kind of like integration. You kind of start to develop more and more of an intuition about how things work the more and more examples that you see and you start to kind of play around with. What I always suggest first is looking at that limit. So if you have a formula, so in our case, we have a formula. This is the formula right here. We have a formula. Let's check to see if this formula tends towards 0 as n gets really big. So we're going to just kind of test for divergence first. Okay, we're going to take the limit as n gets really, really big. 2 to the n plus 4 to the n over e to the n. So where does that go? Well, I mean, we could use L'Hopital's rule. All of these terms are certainly getting very, very large, right? So 2 to the n's getting big, 4 to the n's getting big, e to the n's getting big. All of the numerators tending towards positive infinity, and the denominator is also tending towards positive infinity. So that's something that we could try. I mean, we could try using L'Hopital's rule and see what happens. Is that going to be a helpful thing? That's going to give us what? Ln 2 of blah plus ln 4 of blah over the same thing. I'm not sure that's going to be super helpful. I'm wondering if it's maybe helpful to see what this looks like as a function, right? So remember that when we were working with sequences, we could kind of think about what does that look like as a function. So I think this might be a case where it might be helpful to see what Desmos gives us with regards to, replacing the n with an x and kind of seeing where that goes. So let's try that and see what happens. Because, I mean, I can kind of see that is the case, but you guys might not. So you might want to explore this one just a little bit more to convince yourselves. So here is that function, 2 to the n plus 4 to the n over e to the n. And if we zoom out, we can see that this is, a little kind of parabolic in nature. But certainly as x gets big, this function is blasting off to positive infinity. So in other words, we can think about it this way. The numerator is growing much faster than the denominator is. And in fact, what I always recommended my students do when we were thinking about limits and thinking about limits tending towards infinity is to think about the dominant terms. So, I mean, just from looking at Desmos, we know that this tends towards positive infinity. So, we can kind of write that down here. This would be fine. But for those of you that want just that little bit more, what we could do is we could look at the dominant terms. And so this limit is going to act very similar to the following limit, the limit of 4 to the n over e to the n. And if you kind of factor out that n, okay, using power laws, we get something like this. We get 4 over e to the n. So I'm kind of ignoring the 2 to the n for now because in the numerator, 4 to the n grows much faster than 2 to the n does. So I'm looking at that dominant term in the numerator and comparing it to the dominant term in the denominator. And what I get is I get this number, 4 over e, and that number is going to keep increasing. So this is kind of like, well, let's see. Let's actually evaluate 4 divided by e. That's about 1.47. Ish. I mean, this is kind of like a rough approximation, right? So all of this is just kind of like me background thinking. And I'm thinking to myself, okay, if the base of this decimal number, is bigger than 1, and I allow n to keep increasing, this number is going to explode. This number is going to get really, really big. However, if the base of this decimal number, if it was less than 1, if it was between 0 and 1, then as I keep multiplying it by itself, it's eventually going to get smaller and smaller. So it does, if I want to use this dominant term argument, which is totally fine with me, you want to kind of take a look at, what is the base here? And if this base is too big, when you repeatedly multiply by itself, it just explodes and tends towards positive infinity. Okay, if that base, like I said, if that base is in between -1 and +1, you're pretty much good to go. But if this base is -1, if the base is +1, or if it's like outside the boundaries of a typical geometric series, then you kind of get hosed. You're kind of in a rough spot. And that's what happens to us here. Because the dominant terms lead to a base that's bigger than 1, as we start multiplying that base by itself, that gets really, really big. So that's why this limit is tending towards infinity. So just based on that limit, I know that this is going to be divergent. Okay, if this limit doesn't tend towards 0, I automatically know it's a divergent series. We're not going to be able to associate a sum with this because these terms, the terms that we're adding, are just getting too big at the end. They're not decreasing down to 0 fast enough for us to be able to add up all of these infinite terms. Okay, so this is an example of a divergent series, and like I said, knowing the test for divergence is the fastest way, I think, to show that a series diverges. Right? So if that limit isn't 0, automatically you know it's a divergent kind of series. Okay, number 4. Oh yeah, this is kind of a fun one. No, I don't want to say that. I don't want to say that. Okay, this is kind of a fun one. We're not really going to like prove anything necessarily. We're not going to like... I don't know. I feel like we're kind of like going against what the overall question said, which is, prove if it's convergent or divergent. But what we're going to do is we're going to kind of consider the number 0.999 repeating. Okay? And I want to show you something really interesting about this particular number. So this particular number, 0.9999 repeating, we can think about this number as a sum of fractions, right? So this is 9/10, 9/100, 9/1000, 9/10,000. So we can think about this as a sum of fractions in the following way. And since we have a sum of fractions that looks like this, we can now make, and it's an infinite sum, we can maybe label these as A1, A2, A3, etc. And we can see if these share a common ratio. So let's go ahead, let's calculate A2 over A1. This is 9/100 over 9/10, and we should get 1/10. And let's just double check that the common ratio is satisfied here. And if it is satisfied, if the next ratio we get is also 1/10, this is a geometric kind of series. So A3, which is 9 thousandths, divided by 9 over 100, this is also 1/10. So there's a common ratio. Okay, so as soon as I see that common ratio, I know this is a geometric series. And furthermore, because that common ratio lands in between -1 and +1, I also know that this is a convergent geometric series. Okay, and the last bit of information is we can pull the first term, which is 9/10, and then we can use that in order to find the actual sum. Okay, so the sum of this should be given as a over 1 minus r. We know the first term is 9/10, and in the denominator we have 1 minus r, so 1 minus 1/10. Okay, so essentially I'm just taking this addition of fractions, I'm rewriting it using the converging geometric series formula, and look at what happens. We get a 9/10 in the numerator, we get a 10, so we get a 9/10 in the denominator, and we get 1. So if we come back up here and we look at the left-hand side, what have we actually proven? We've proven that 0.999 repeating is actually equal to 1. And I think that's interesting. I don't know if you guys have ever come across a proof of this before, but this is true. Like, I'm not trying to like blindside you or pull your leg or joke around. This is a very, very truthful equation. This has to be true, right? Based on our geometric series formula. And it kind of boils down to this interesting idea that we have like a decimal representation and a fractional representation of the same number, right? So 0.999 repeating is one possible decimal representation of the number 1. I also like to think about the number 1 as a fractional kind of representation of this number as well. So yeah, 1 has other ways of expressing itself, and this is one of those kind of interesting mysteries of infinity, right? Because there are an infinite number of 9s. Turns out that it's not close to 1. It actually has to be equal to the number 1 in order for mathematics to work. So I think that's a very interesting kind of thing, and you can maybe play around with other numbers, like, you know, is like 1.999 repeating, is that really equal to 2? I think you can probably show that that's true. So yeah, so I think this is inside the textbook. I thought it was a kind of an interesting kind of example. I did want to show you that. That was number 51 from the textbook, in case you wanted a reference. So. Okay, number 5 here is question 17 from the textbook. I picked this one because it talks about telescoping series. And I think this is, I mean, if you see this terminology, it kind of gives you a hint on how to find the sum of the series. So a telescoping series is one where we have some additions and some subtractions happening, and it turns out that sometimes the subtractions and additions will cancel out each other and give us 0. So basically, a telescoping series is one where some of the additions and subtractions will end up canceling. And number 17 had a very kind of straightforward and relatively nice example to look at. So here we have the sum as we go from 1 to infinity, and we have a sum of fractions. We have 1 over n plus 2. And we have negative 1 over n. So, like I was saying a couple examples ago, what I would probably try to do first is I'd probably try to test for divergence. Especially if I'm unsure about whether or not this is a convergent or a divergent kind of sum. And testing for divergence says we should set up the limit as n tends towards infinity of the formula, and we should see where this limit goes. And of course, as n gets really large, we get 1 over a really large number, which is 0, and we get a subtraction of 1 over a very large number, which is also 0. So the test for divergence doesn't really give us any information, because whenever I get a limit of 0, that's something that I should expect. It doesn't mean that my original series has to converge. It just tells me that the series doesn't diverge. Well, that's false. It tells me that I can't conclude that the series diverges. Okay, so it still could diverge, it still could converge. I don't really know based on the test for divergence. So what the textbook tells us to do is to start subbing in some values for n and see what happens. So because I have a minus sign here in between the two fractions, it's quite possible that some of the fractions we get will cancel off with some of the other fractions that we get. So let's go ahead and start putting in indices in here. So for n is equal to 1, we get 1 over 1 plus 2, which is a third, and we get 1 over 1. So this is the term that we get for n is equal to 1. And let's kind of keep going. So let's next try n is equal to 2. That would give us 1/4 minus 1/2. So this is the two terms we would get for n is equal to 2. And maybe I'll do a couple more. So let's do n equals 3, which would be 1/5 minus a third. And I'm hoping that after we do one more, you can kind of start to see what's going to happen here. Okay, so that's the first kind of 4 indices. And what we want to do is we kind of want to look at the different fractions that we're getting, and we want to see if any of the positive fractions are going to match up with a negative fraction of the same size. So taking a look at this positive 1/3, I can kind of scan through my negative fractions, and I see that a negative 1/3 pops up over here. So this 1/3 will cancel, well, when we add these together, they will add up to 0. So those two terms are going to disappear. Next, let's take a look at our positive 1/4. And we kind of, again, are going to scan through our negative fractions, and we see that we have a negative 1/4 here. So these two fractions would add up and give us 0. And what we're going to see is that all of our positive fractions, this 1/5 would match up with a negative 1/5 that happens somewhere in here. So that one's going to cancel. This 1/6 again is going to line up with a negative 1/6 that we might get. So that's going to cancel. So it's going to be kind of like little dominoes. Like a bunch of our positive fractions are going to disappear because they're going to match up with a bunch of the negative fractions that appear. And then we're going to be left over with negative 1 minus a half. Those are the two fractions that are left over. I'm going to circle them here in red. Those are the leftovers. So because they're the only terms that are left over, I can add those together, and that's going to be the sum of this particular series. So this is called a telescoping series because some of those positive fractions end up canceling with some of those negative fractions. And the last kind of technique that I want to show you for the class today is this idea of utilizing partial sums. So I want to talk a little bit more about what this means because this technique is introduced inside of this chapter, and I think it's an important one for those of you that are going to continue on in mathematics to think about. And I want to do it through the following example. So number 8 from this section looks like this. We have a sum from 1 to infinity of negative 1 to the n times n. So to get our partial sums, because our lower bound here starts at 1, we're going to start our upper bound at the same number as our lower bound, and we're going to kind of keep increasing it by 1, and we're going to kind of keep track of these sums as we add more and more terms. So for example, we would say our first partial sum, we're going to call this S1, and S1 is defined to be the following expression. We're going to use the same upper bound as the lower bound, so we only have one term to think about, and that is the term that we get from subbing in 1 into this formula. So that's going to give us -1. Okay, so our first partial sum is -1, and our second, we call this S2. That's the typical notation we use. And for S2, we're going to increase that upper bound by 1. In other words, we're going to take this first term that we got, and we're going to add to it one more term. Okay, so we know that this first term is -1, and we're going to add to that -1 squared times 2, so we're going to add 2 to that, and that's going to give us 2 minus 1, which is +1. And so let's do this a couple more times. And then what we do is we kind of analyze these partial sums to see if the partial sums are going somewhere, or if they're not really going anywhere, if they're getting larger and larger. So the next partial sum would start at 1 and end at 3. And that's going to give us -1 times 1 plus -1 squared times 2 plus -1 cubed times 3. So we get -1 plus 2 minus 3. So that's going to be -4 plus 2. So it's going to give us -2. Okay, one more, and hopefully we'll start to kind of see a pattern in these partial sums. So the fourth partial sum, of course, would start at 1, go up to 4. Okay, so we already know the first few partial sums. We get -1 plus 2 minus 3. And you can show yourself that we're going to essentially be adding 4 to this. So that's going to give us 6 take away 4, which is 2. So hopefully you're going to start to see a pattern arising inside of our sums. We start at -1, then we go to +1, and then we go to -2, and then we go to +2. So the sequence of sums that we get is -1, 1, -2, 2. And you can probably see where this sequence is going. We should get is it -3 next? I need to be careful that I'm not actually going up by 2's here. So the next one would be -5, so it would be 8, 9, and 6. Yeah, so it's going to be -3, +3, then -4, +4, and so on and so on. So these are the sums that we're getting as we start to increase that upper bound. And you can see that as we start to increase that upper bound more and more, the sums that we're getting start to get larger and larger. They do fluctuate above and below the x-axis, but we kind of get something that looks like this, right? If this is our x-axis, we're getting like -1, +1, -2, +2, -3, +3. So we're getting something that is looking like this. So our sums look like they're kind of getting bigger and bigger as we start to move towards the right. So we're adding or subtracting larger and larger numbers. So this has to be a divergent kind of sum because this limit of partial sums is not tending towards 0. So this is the last technique that I really wanted to show you. And if all else fails, you can always start adding up things term by term, looking at that sequence of sums and checking to see if that sequence does tend towards some kind of number. So if these partial sums do tend towards some number, then that gives us an indication that maybe we should be able to prove convergence. But in this case, we looked at those partial sums. It doesn't look like it's tending towards a number, so that's going to kind of force us to conclude here that the sum that we started with is indeed divergent. Okay, another way to do this would be to test for divergence, and that is to check the limit as n tends towards infinity of the following. You should be able to show that this does not exist, right? So one or the other, right? So we can check the partial sums, or we can look at the limit of the formula. And ideally, one of those things is going to lead us to the idea that this has to be a divergent kind of sum. Okay, so those were the main examples I wanted to cover from this section. So for the lesson on Friday, we're actually going to start looking at the definition of integration. So when we started looking at integration, we kind of hand-waved a little bit and said, hey, it's kind of like a sum of stuff. So I want to go back and now that we've dealt a little bit with summation notation, I want to kind of dial back our work with integration, look at it as a sum of rectangles and see how those things are connected to each other. So we're going to do a little bit of an introductory class with regards to the definition on Friday. So yeah, you guys hopefully have a lovely rest of your week, have a lovely weekend, and I will definitely catch up with you on Monday. And like I said, if there are any questions that you have over the next couple days, just let me know. And we can either answer those questions by email or find a time for us to get together. Okay. So have a lovely rest of your day, lovely weekend, and I'll see you guys on Monday for sure.